Hello and welcome to episode 6B of our physics lecture series. And today we're going to be looking at calculating the center of mass of a triangular lamina. So, for reference, I'm going to write down our equation. So we have our R dm over our object over the integral dm over our object. So what we want to do is we want to solve this want to figure this out. So let's quickly analyze this diagram I've drawn. So we have our y-axis and x-axis, and we have this y-axis, or the x-axis splits our triangle in half perfectly. It has a length. It's going to be the height of the lamina, and we're going to be giving it this upwards angle. So why do we cut it in half? We don't care about this upward angle. Well, that's because since it's cut in half, we only really need to consider the top half. We can actually, because of symmetry, we can say that the center mass in y is equal to 0. Right? Because that's right down the center. So with that in mind, this r becomes less complicated. We only really need to think about x. So what is the center of mass in x? And that's what we're trying to find. So to do this, we need to think about a few things. So what the hell is this dm? So if you recall from the sort of discrete version, we want to, or if you remember, this dm is really just a box. It's a tiny, tiny, tiny slice. It's the mass in an infinitesimally tiny slice. Right? So this is what I'm going to do. I'm going to take a slice. I'm going to call this dx. So this is a tiny, tiny, tiny change, and this dm is equal to the mass in this tiny, tiny change. So we have dm equals something times dx, right? So I'm going to define this constant, sigma. This is going to be the mass surface density, and it has units of kilograms per meters squared. This is essentially the mass over the surface area of our object, right? So this is going to be that mass surface density, and what I'm going to claim here is that dm is equal to this mass surface density times the area of this tiny, tiny slice. So let's think about what this area is. So I'm going to write down this. So we have some arbitrary r, or h, right, for the hypotenuse. And we want to get this side length. Well, this guy right here, this is going to be this x. So it's going to be this purple x. You have this identity, purple x is equal to h times cosine theta, right? Hopefully that shouldn't be too surprising. We can rearrange this to find h equals x over cosine theta. And now this side here in purple, this is equal to h sine theta. Right, and so the reason I write h here in terms of x is because we don't know what h is, and we don't want to integrate over h, we want to integrate over 8x, right? Because integrating over h is going to require us to integrate over x and y, right? It's equal to x squared plus y squared square root. We don't want to integrate over that. We want to write this exclusively in terms of x. So x over cosine theta. And when we substitute this in, we find h sine theta. Well, this becomes x sine theta over cosine theta. This is equal to x tan theta. So that's that line, x tan theta. Okay, so we had this equation. We're going to be this times area. This is going to turn into, so remember we actually have two sides of this, so we have 1 and 2. It's going to be 2 times sigma times x tan theta times dx. And this is equal to dm. Right? So we actually have enough to calculate our first integral. Our bounds is going to be 0, 0. First integral we want to think about is going to be dm over our object. This is equal to this single integral from 0 to L of 2 sigma x tan theta dx. And so what is this integral? This is 2 sigma L squared over 2 tan theta. And so these cancel out. And we are just left with this side. And so we can, this is going to be equal, and this is equal to big M. Now we want to calculate our position here. The top half is going to be very similar. 0 to L, and here we're considering x dm, or over our object x dm. This is going to be integral from 0 to L of 2 sigma x squared tan theta dx. And what is that? Well, then that's just 2 over 3 sigma x cubed, or not x, L cubed tan theta. Alright, so we have enough to plug these in, put these together. We get 2 over 3 sigma sigma tan theta x cubed, or not x cubed, L cubed L squared. What happens? Well, most of these terms cancel out, and we end up left with 2 over 3 L. And this is equal to the position of our set. This is actually equal to the position of x. So I'm going to go big X. And our center of mass is equal to big X, big Y here. So our center of mass, which is 2 over 3L and 0. Right, so that's that. This is the position vector for our center of mass. All right, that was very quick. Hopefully that derivation made sense. In the next part, we're going to be looking at a solid cone. So we're actually going to look at a 3D example. See you then.